Next speaker will be McGreevy from UCSD, and he will tell us about the entanglement bootstrap. Yeah, John, please go ahead.
Great. Can you hear me?
Yeah.
Okay. So yeah, thanks so much for having me. I want to tell you about some recent progress with our wonderful UQM postdoc Bowen and with my student Jinlong Wang. And one way to motivate our project is the following question of principle. Suppose someone gives you just the reduced density matrix on a ball of some representative ground state of some phase of matter. Can you extract all of the universal properties of the phase just from that data? And so we'll be a little bit less ambitious and ask the question in the context of a topologically ordered ground state, a gap topologically ordered liquid ground state, and try to extract all of the information about the effective topological field theory that governs the universal low energy physics. And I guess a few precedents for successes in this direction are the topological entanglement entropy, which can be extracted from some combination of entropies, for example, in a configuration like this, from the reduced density matrix on a ball, and encodes the total quantum dimension of the excitations. And the modular commutator that Bowen talked about yesterday, which from slightly more refined information about the reduced density matrix, again on just a ball, extracts the chiral central charge. So those are some those are two let's say coarse invariants of the effective topological field theory. And the entanglement bootstrap program is the goal is to extract all the rest of it. And there's an apparent obstacle to doing this, to extracting all of the topological field theory information, which is that a topological field theory, as we heard, for example, from Dan Fried yesterday, it's a machine that eats interesting manifolds and spits out topological data. And you might think that if we only have access to the wave function on a ball, how can we say anything about about the partition function on RP3 or on some whatever crazy manifold you're interested in? So I want to explain. So my main goal in this talk is to explain a method to overcome this obstacle, which is a sort of quantum avatar of what's known in topology as Kirby's torus trick. If you don't know what that is, I'll tell you. And then I want to use that that technology to understand what might be called braiding non-degeneracy or remote detectability, which is it's an axiom of topological field theory that's a theorem of the entanglement bootstrap, which roughly says that any topological excitation, meaning any excitation that can't be created locally, which in 2+1 dimensions would be an anion, can in fact be detected remotely by some other topological excitation. So that is, in particular, participates in some unitary S matrix. And for each class of excitations, we'll do this by we'll define the S matrix in terms of an auxiliary closed manifold associated with that class of excitations, which we call a pairing manifold. So this definition is sort of the star of the show, which in the case of bulk anions in 2+1 dimensions is just the 2 torus, as perhaps you might expect. And this turns out to be a pretty fruitful concept in many ways, actually surprisingly fruitful to me. For example, it can be used to count excitations of various kinds. It gives some more insight into the structure of topological entanglement entropy, in particular in above 2 dimensions, 2 space dimensions, there's more than one notion of topological entanglement entropy. And this gives us some insight into relations between them. And it leads very directly to the Verlinde formula, as I'll explain a little bit. And one surprise, to answer a question that Nadia asked me quite a while ago, is in general, actually, there's no relation between these S matrices that I'll define and the mapping class group of the analog of the torus here. Only in special cases is there such a relation. Okay, so that's the preview. So let me back up a little bit. And so in this question, I said, we're going to start with a single topologically ordered ground state wave function. And I need to answer the question. In order to do that, we need to answer the question, well, how do we know that it's a ground state wave function? So in particular, I'm not going to specify anywhere in this talk any Hamiltonian, which, you know, is the kind of thing that generally drives condensed matter physicists crazy. But if you'll have to forgive me, because so the way I'm going to implement the fact that the wave function I'm talking about is a ground state wave function is by a couple of axioms, the entanglement bootstrap axioms, which enforce the area law. In fact, a sort of strong form of the area law. So more specifically, I'm going to demand that on any disk, actually we can you know, imagine we start with a lattice model and only demand that it's true on a small disk compared to the lattice space, you know, just a few lattice spacings, that this combination of entropies, which I'll call delta BC, vanishes. So that's a saturation of the Araki-Lieb inequality, if you like that language. And also that this combination of entropies vanish. So for any, you know, draw any ball on our, that's part of our disk where we have the wave function, and demand that these two things are true. And a few things that these folks showed follow from those axioms are, well, in particular, you can enlarge the axiom. So if the axioms are true for small disks, they're also true for larger regions that have the same topology as these combinations of BC and BCD. And
excuse me, I have a question.
Oh, great. Yeah, hi.
So this A0, A1, they vanish. Do they vanish exactly for lattice model?
Great.
Or they only vanish approximately in the thermodynamic limit?
Yeah, that's a very important question. So that's my second comment here. So actually, this is a stronger condition than is actually true for an arbitrary point in some gapped phase. It's true for fixed point wave functions. This is exactly true. So some phases have a representative wave function where these axioms are exactly satisfied. But more generally, we expect and I think we can show that the axioms are asymptotically true, so that the violation of the axioms at, you know, in a point in the phase diagram where there's some given correlation length decays exponentially, maybe something like twice like with a rate which is something like twice the correlation length. So you should imagine that if you want to study an arbitrary point in the phase, you should just take really big regions. So that the axioms are you know, asymptotically close to being true. Yeah, that's a very important question, and that's actually a a hole in the discussion. So that's a hole that we'd very much like to fill in, but have not yet. Because yeah, we're gonna use the exact axioms to prove things, and as you probably know, the key properties from the axioms is that various things are going to be quantum Markov chains. There are generalizations of the theorems about quantum Markov chains to approximate quantum Markov chains, but they haven't yet been optimized for what we need, and so there's something to be done there. Yeah, so that's a very important codicil to everything I'm going to say, actually.
But however, the result you obtained would apply more generally in the sense for the topology order, which is not realizable by stabilizer code. Is that right?
That's the expectation. Yeah, that's right. So I expect it also applies, for example, to chiral states. That's right.
Okay.
But I don't know how to show that. Yeah, thanks, Jung. Okay, so a little bit of intuition about the axiom. So one way to think about A0 is that it implies that if I draw any region A in the complement of this disk, you can think of B as a buffer between C and that region A, and it implies that the mutual information between A and C exactly vanishes. So this shows you that since the mutual information between A and C bounds correlation functions between A and C, it shows that we're assuming that this is only exactly true for zero correlation length. And then A1, similarly, you can think of B as a buffer here. Again, if I draw any region A outside of this disk, it implies that the conditional mutual information, the mutual information between A and C conditioned on B, vanishes exactly. So that is, the state is a quantum Markov chain, which implies various very strong properties. And the relation to the area law I should mention. So A0 directly implies the area law for round balls. So in particular, if I take the region B to be only a little bit bigger than C, then the vanishing of this implies that SBC is only a little bit bigger than SC. In particular, it's bigger only by an amount which is SB, which is bounded by the volume of that thin disk. And then combining A0 and A1 together shows that an area law is true also for arbitrary shape regions. It allows us to change the shape of the region. And it implies that the subleading term for the area law is some universal thing. So it rules out these sort of fake, these sort of Bravi counterexamples associated with subsystem symmetries. Okay, so those are the axioms in 2 dimensions. And this sort of central ingredient in the entanglement bootstrap is this object called the information convex set, which is a machine that associates to an arbitrary region of space. Think of it, let's say, an arbitrary subregion of the ball that we started with, a convex set, which is the set of density matrices on that set. So here's an example of a set X, which are indistinguishable from the reference state, from the given reference state on balls inside the region X. This is an interesting thing because even though we're demanding that the state is essentially the ground state on this annulus, for example, inside the region X, there can be excitations outside the region X. So for example, in 2 dimensions, if our region is an annulus, there could be an anion inside this annulus attached by its string operator to its antiparticle. And the fact that the string operator has to cross the annulus means that the density matrix of the annulus globally knows about that the anion is in there, even though locally that information is not detectable. And this information convex set is a topological invariant in several senses. Well, so provably, it only depends on the topology of X in the sense that the information convex set of some region is isomorphic to the information convex set of any region that's related to it by adding or removing small balls. And what I mean by isomorphic here is that the structure as a convex set is the same, and also the entropy differences between, let's say, extreme points of the convex set are the same, and fidelities are the same. So it's as the same as you could want for these convex sets of density matrices. And then we expect that it should be insensitive to small changes of the reference state within the phase. So this should be is related to Jiagong's question. So because the correlation length will change if you move around within the phase, but we expect that such a statement is true, at least for large enough regions. Okay, so that's the information convex set, and a few key results in the case of the 2-dimensional entanglement bootstrap, which you can find in this lovely paper, are the following. So first of all, the information convex set of the annulus is a simplex, and its extreme points are orthogonal, and these extreme points can be associated with anion types. So an extreme point, think of it as associated with creating a particular kind of anion, the state associated with creating a particular kind of anion inside the annulus. The information convex set of the 2-hole annulus produces, in a way that I'll explain more in just a minute, some Hilbert spaces of integer dimension called NABC associated with the 3 anion types on the 3 boundaries of the 2-hole disk. A notion of quantum dimension can be defined in terms of this difference of entropies from the reference state. So row 1 here is the state of the annulus that you get just by reducing the reference state. And this definition of quantum dimension agrees with this, is consistent with this notion of fusion dimension. It's the positive solution of this equation, which is the usual definition of quantum dimension in modular tensor categories. Okay, and then finally the TEE is related to a particular conditional mutual information in the ground state, and and as usual is related to the total quantum dimension. Okay, so that's in 2 dimensions. And these axioms.
I have a question here. Could you explain how do you get a set of a density matrix? Because you say you have a sphere, you have only one state. If you carve out the region, they only get one density matrix. So I'm a little bit confused. How you
there's only indeed, if you just take the reduced density matrix of the given reference state, you just get a unique density matrix on the annulus, which is what I'm calling this row 1, the vacuum state. But the information convex set contains a whole bunch of other states, in particular the ones where there are excitations elsewhere in the ball, but outside the annulus. right? So like in this picture, I'm acting with some string operator, where so the string operator preserves the vacuum, say commutes with the Hamiltonian in the interior, but at its endpoints, it creates an excitation. So this state is distinguishable from the vacuum here and here, but it's indistinguishable from the vacuum everywhere on the annulus. And so this produces a different density matrix. In fact, it's orthogonal to this reference state. And for different A, it's they're orthogonal to each other, which are elements of the information convex set.
Can I say that, let me try to see. Well, for the reference state, you only have a one density matrix. And then the other density matrix, you want to include the other density matrix, which are locally indistinguishable from your reference one.
Exactly.
Then that's from a set. Okay,
exactly.
so you enlarge that by including every other one which are locally indistinguishable. Okay, thank you. Yeah.
Exactly. Yeah. Great. Thanks for the question. Okay. So these axioms, I just described what happens in 2 dimensions, but in fact, a very similar story obtains in any dimension. In 3 dimensions, a set of axioms which produces the same machine is just to consider, again, BC and BCD to be balls, and B is just the thickened boundary of this ball here, and here B and D are the thickened boundary of the ball just cut in half. So each of B and D here is topologically a ball, and the same is true in any dimension. In 3 dimensions, you can think of it as the volume, the volume of rotation. And with these axioms, the basic results generalize. In particular, the axioms can be enlarged. The information convex set is invariant under deformations of the region. And now we can ask, well, what generalizes the annulus for classifying the topological excitations, say in 3 dimensions? So again, there can be particle excitations, which are detected by a sphere shell. The sphere shell surrounds a particle. And there can be loop excitations, which are detected by the information convex set of the solid torus. So here's a solid torus, and an excitation which is created by a membrane operator whose boundary links with that solid torus creates an extreme point of the information convex set of the solid torus. There are some more general excitations. For example, we can consider the information convex set of the torus shell, and which is sort of a combination of 2 loops and some particles. But there are actually much more different excitations in 3 dimensions beyond these. For example, you can think about there are 2 ways to fuse together 2 loops. So one is just to put them on top of each other, but a more interesting thing is to fuse them along some segment here to produce something that's shaped like a graph, where the excitation is shaped like a graph. And this leads to a new family of sectors, which are detected by the genus 2 handle body. So by that, I just mean the inside of a genus 2 Riemann surface. And you can see here that its complement is it's homotopic to this red curve here. And this information convex set is also a simplex. And you can see that it's not just sort of a 2 loops stuck together. For example, by considering the example of the quantum double model, where we can do everything essentially arbitrarily explicitly, we can compute the number of extreme points for the genus G information convex set of the genus G solid in terms of various, some sum over elements of the centralizer of the element of the group. And for example, just to be definite, take the case where the group is just S3, then the genus 2 information convex set gives 11 extreme points, whereas there's only 3 loop types. So putting two loops together gives only 9 possibilities. So there's 2 more things which aren't just obtained by putting 2 loops near each other. And then there are more things. So for example, we can consider an excitation which is shaped like a knot or a link, which are detected by the respective knot or link complement. Or for example, we can think about excitations which are a particle and a loop, which are correlated somehow, meaning they're created by an operator which is sort of part membrane, part string. And that's detected, for example, by the information convex set of a torus with a ball cut out of it. The particle goes inside the ball, the loop links with the torus. Okay, so you can see that there's a sort of very rich story about possible topological excitations and what regions detect them. And so we need to try to organize that a little bit. And so one very important dichotomy about what is the structure of the information convex set of a given region is between whether that information convex set contains classical data or whether it really contains quantum information. And a class of regions which are called sectorizable, so this is just a geometric property of the region. In that case, the information convex set is a simplex. So that means it only stores classical data. And this definition of sectorizable is really exactly the condition that you can copy the data. So here's a picture of the annulus. The key point is that the annulus can be divided into two pieces, each of which has the same topology as the annulus itself. So a region is sectorizable if it can be divided up into two disjoint regions. So here I'll denote disjoint union just by writing the sets together. And where both the subsets L and R can be extended, so by adding little balls to get back the original region. So in that case, the information convex set only contains classical information. If that's not the case, however, then the information convex set of the region contains quantum information and in the form of fusion spaces. And so here's the more general statement. The information convex set of an arbitrary region can be decomposed into a convex combination, that's what I mean by this plus sign, of subsets labeled by extreme points of the thickened boundary of the region. So here's a region, its thickened boundary is like this. The thickened boundary is always sectorizable. That's a fact. And so this thing is always a simplex, which has some set of extreme points. And in each of these sectors where I fix the data on the boundary, the information convex set here is isomorphic to the state space. That's what I mean by S, the space of density matrices on some Hilbert space. V sub A labeled by the extreme point of the boundary, and that has some dimension, which is a non-negative integer, which is some invariant. Okay, so that's the state inside that vector space is some quantum information encoded in this information convex set. Okay, so for example, the ball minus two balls is not sectorizable, and it contains this fusion data that I was just describing. Okay, so I think I have two more tools that I want to talk about before I get to the story about making closed manifolds. Or maybe just this. And the key extra ingredient is called merging, which is the following statement. If I give you two information convex sets, the information convex set of AB and the information convex set of BC, and ask about a state on AB and a state on BC which agree on B, so the reduced density matrix on B is the same, then they can be merged to make a unique state on ABC, which moreover has the following nice properties. It's a quantum Markov chain with respect to B, and it's the maximum entropy state in that information convex set that's consistent with its marginals on AB and BC. And moreover, the merging process preserves entropy differences. So this is a very powerful tool. And a special case of it is what we call the associativity theorem, which is the statement that, so suppose that B, the region along which we're joining these two things, let me call them omega left and omega right, is a whole boundary component of each of those regions. So for example, suppose that omega left is this thing here, and omega right is this thing here. So B is this annulus here by which they're joined. So that's what I mean by a whole boundary component. In that case, the fusion dimensions are related by convolution. So just sum over all of the possibilities for what's happening in B of the dimensions of the fusion spaces of each of the constituents with the given boundary conditions. So this reduces the complexity in the sense that we can make bigger regions from smaller regions, and the structure of the fusion spaces of the bigger regions is fixed. And this is called the associativity theorem because in the case of particles in two dimensions, exactly this relation, the merging of these regions and these regions, gives this associativity relation between the fusion dimensions. So it's named after that example. All right, so that was a brief summary of entanglement bootstrap. And now let me try to tell you about this business of making closed manifolds. So the key first step is this notion of immersions. So immersion is a word from differential topology, which generally implies some kind of smooth structure. And I'm going to use that word because I do want to convey that you know, the maps I talk about, I don't want to talk about like horrible pathologies like Alexander Horn spheres. So I'm just going to talk about as if there were a smooth structure. Okay, so the key idea is we can define the information convex set for some region of W, which is actually not a subset of the ball. So a good example to think about is this little monstrosity here, which is going to be important. So you see so think of this whole thing as living inside the ball, but on this locus here, the region W is a double cover of the ball. So there's, you know, for every point on the ball here, there's 2 points in the region W. And this is a version of what's called the Kirby torus trick, which let me tell you what that is. So the idea is given an immersion, I guess, of a manifold into a ball of the same dimension. I guess maybe I'm supposed to call that a submersion. I'm not sure, but I'm going to call it an immersion. We can pull back structure from the ball to the region that's being immersed, to the manifold that's being immersed. So by pullback, I just mean, you know, given some function on B, the pullback of that function is a function on W defined by f of the image of the point W, right? Just the usual pullback. And Kirby used this idea to pull back smooth structure from the ball to the manifold he was studying, which was actually the torus, or maybe piecewise linear structure, I'm not sure, or maybe both. The same idea was used not too long ago by Hastings to pull back a local Hamiltonian for an invertible phase for his own nefarious purposes. And we're going to use it, the idea to pull back the reference state on balls. So that we can compare, so given a state on W, I can use the reference state on the big ball to compare locally the data on the wave function on W to on a little ball to the wave function on the big ball. So a few comments. So given some general immersion, if I just draw some picture like this, it's not obvious that the information convex set of that manifold is non-empty, and it's certainly not obvious that it contains a vacuum state, some analog of the reduced density matrix of the reference state. But one thing that we do know is that the isomorphism theorem generalizes. So that is, regions that are related by regular homotopy, that is a homotopy where each point in the family of maps is also an immersion, have isomorphic information convex sets. So the same statement that the information convex set is independent of the topology of the region applies if you deform it through immersion. So the regions are allowed to overlap with each other. So this shows, for example, that the information convex set of a knot is the same as the information convex set of a solid torus for any knot. Okay, so that was step one. Step two is filling in the holes. So I guess, yeah, first I should explain why is that trick called the torus trick. And that's because this region that I drew is actually a torus with a hole. So here's another picture of a torus. Here's a torus with the hole. And here's another representation of it in the square with opposite sides identified. So you see, if I take the whole thing, it's a torus. And if I cut out a hole, this is a hole. You see this thing has a single boundary. Then I get this region. And maybe it's not too hard to convince yourself that that's the same as this. The intrinsic topology is the same. And so by studying, by immersing this region in the ball, which is what this picture does, we can pull back structure to the punctured torus. And then if we can fill in the hole, then we get that structure on the whole torus. And so that's the second step of Kirby's trick. And we can do that too. In particular, if the boundary is the thickened boundary of this thing, which is this whole single component of the boundary of this object that I just traced out with the cursor, is in an abelian sector, meaning that the quantum dimension of the state of the thickened boundary is 1, then we can fill in the holes to make a reference state on the whole closed manifold. Okay, so and indeed with some assumptions, we can guarantee the existence of a vacuum sector. So that is, there's a large family of examples where we can guarantee the existence of such a vacuum sector on the boundary W of the immersed region so that we can fill in the hole and make a closed manifold. So for example, on the disk, there's the reference state, of course, is in the identity sector on the boundary. And so this hole can be filled in to produce a sphere. And this is a very useful trick because, you know, if you're allowed to deform things on the sphere, you can turn various things inside out. So that becomes a useful tool. And in the example of the torus with a hole, because we can make this region out of these kinds of building blocks, where each of the thickened boundaries of these regions is, well, at most one of the thickened boundaries of these regions is not embedded, we can guarantee the existence of a vacuum sector on this boundary and therefore fill in this hole to make the whole torus. And one way to see that this is the case is to consider this green thing, which here is drawn in blue. On even on the ball, it looks like this, and I can deform it. So first move this guy over here to get this, and then move this thing inside this hole, so to get this. And so you see it's just a two-hole disk. And if I choose the sector B to be 1, then there's a unique state where these two boundaries are 1, and that forces A to be the vacuum. And so, well, anyway, this is a proof that we can guarantee that this sector A here is in the vacuum, and therefore we can fill in the hole. So let me introduce a little notation. I'm going to call a vacuum completion the following. I guess it's a triple of a closed manifold. That's the manifold that we're building at the end. A collection of building blocks with the property that we can guarantee that the thickened boundary that remains when we glue them together is in a abelian sector, and an immersion, which is the region that we get by gluing together the building blocks. So it's this thing is the manifold minus potentially a bunch of holes. Okay, and given those ingredients, there's a unique canonical state, a pure state in the fusion space of that manifold. So that's you know, the information convex set of the manifold is the state space of some vector space, and that reduces to the reference state on the building blocks. Okay. And so another example is we can make a genus G Riemann surface by gluing together these ingredients. So these are the building blocks, and so there's a yeah. So in fact, we can make an arbitrary oriented Riemann surface in this way. So now a little more ambitiously, let's talk about some examples of making closed manifolds in 3 dimensions. So one that'll be very important is S2 times S1. So here's some building blocks by which you can make S2 times S1. So this one is two sphere shells. So this one is just a sphere shell, which you should think of as the inside here. We're going to stick it inside here. This is 2 sphere shells where the inside of one is glued to the outside of the other one. And to convince yourself that, so this thing has a single boundary, and to convince yourself that if you fill in that boundary with a ball, you get S2 times S1, here's a series of instructions. So one way to think of the 2 sphere is by taking two balls and disks and gluing them together along their boundaries like this, right? That gives you a 2 sphere. And so think of S2 times S1 as take a ball times a torus and glue each of those balls in the way that we did here, right? So glue this, so this gray thing and this gray thing is a copy of this picture. I glue them together along. So I take these 2 solid tori and glue them along their boundaries. So that gives me S2 times S1. And if I remove a ball from this, I can enlarge the thing I've removed so that all that's left is this orange tube. So the thing that's left is this orange tube, and this ball times an interval glued to this ball times an interval. A ball times an interval glued in this way to a ball times an interval is S2 times an interval, which is a sphere shell. That's this sphere shell here, or yeah, that's this sphere shell here, and this orange tube connects its inside to its outside. So okay, so I'm not sure if that might have been too fast, but this was sort of a visual proof that if you fill in this hole, you get S2 times S1. The same technique works starting from a ball minus 2 balls to make connect sum of S2 times S1. G times. So connect sum means to connect sum of two manifolds means you remove a ball from each of them and then glue those two the spheres on the boundaries of those balls together. Okay, so there's a large class of other examples, which I don't want to overwhelm you too much, but I want to impress upon you that there's a large class of examples that work. And one important generalization is that we can generalize the entanglement bootstrap to cases where there's a gap boundary. So the appropriate generalization of the axioms was studied by Bowen and Isaac Kim in this paper. And so then there are two kinds of boundaries. There's the entanglement boundaries that I've been talking about so far, and then also the gap boundary, which sometimes I'll denote by this furry boundary here to distinguish it from the entanglement boundary, which are just ordinary lines. And in this way, we can make various other manifolds. For example, we can make manifolds with boundary, like a cylinder with two boundaries, or a pair of pants. In 2 dimensions, or in 3 dimensions, we can consider a pure state on, say, a solid torus with a gap boundary, or a sphere shell with a gap boundary. And we can make reference states by this procedure of vacuum completion that I described. Okay, so let me make some differential topology comments. Which manifolds can we make this way? So as I said, every orientable 2-dimensional manifold can be made this way, including with boundaries. But which 3 manifolds, which closed 3 manifolds can we make this way? The existence of an immersion of some open manifold into the ball of the same dimension is possible if and only if the tangent bundle of that open manifold, this thing I've been calling W, is a trivial bundle. So it doesn't demand that the whole closed manifold has a trivial tangent bundle, like the sphere, for example, has a non-trivial tangent bundle, the 2-sphere. But if you remove a ball, then you can immerse it in the ball because it actually is a ball. So this possibility of removing a ball is quite powerful here. Yeah, this theorem I think is roughly due to Smale and Hirsch. But in fact, okay, I think there are closed-oriented 3 manifolds whose tangent bundle remains non-trivial no matter how many balls you remove. And the example that I have in mind is the nil manifold, which is some torus bundle over the circle. So just this is a proof of principle that there are some manifolds that we can't, or at least we don't yet know how to make in this way. So that's an interesting hole in our understanding. However, in that regard, it's worth noting that generalizations of this technique are possible. So for example, rather than starting with a reference state on the ball, satisfying the axioms everywhere, we could allow some violations of the axioms in various places, meaning that there can be defects inserted. And we can still study this notion of immersion, even in the presence of defects. Okay, it'll require some generalization, but there's room for improvement here. So I have some optimism that well, everything is included. Okay, so that was a bit of technique, right? So that's a way to, starting with just the wave function on a ball, to access information about the same state of matter on perhaps not arbitrary, but a large class of closed manifolds. And so here's an application of that technique. So let me just start by defining what I mean by a pairing manifold. So a manifold, closed manifold M, and by closed I mean I'll allow gapped boundaries. So but no entanglement boundaries. Is a pairing manifold if it admits 2 vacuum completions, if it can be built in the way that I just described in 2 different ways, which are sort of conjugate to each other in the following sense. So it's a little complicated, but please bear with me. So M can be decomposed into X and its complement, where X is some region of interest, such that this is a vacuum completion in terms of some immersion W. So here's a picture of, say, making the cylinder with 2 gap boundaries by gluing together various regions. So here's the immersion W, which is the cylinder minus a ball. And X in this case is this purple region, which is like a half annulus, an annulus that's been cut in half by the gapped boundary. It admits a second vacuum completion, so that is M can be cut in half as Y in its complement, which is, it's again a vacuum completion with the same immersion. And in this example of the cylinder, that's like cutting the cylinder in half in the other direction. So here we're cutting the cylinder in half vertically, here we're cutting it in half horizontally. And the W is the same, the immersed region is the same, but now the region Y is this annulus surrounding the gap boundary. So it's a annulus cut in half along a different cycle by the gap boundary. Okay, and what I mean by conjugate, these two ways of cutting in half, cutting M in half, are conjugate in the following sense. So we demand that all of the intersections between X and Y and their complements, and every combination of X and Y and their complements, all the intersections have to be balls. And that condition, it says that the information in a density matrix on X is totally hidden from the information in the density matrix for the information in Y, because the reduced density matrix on Y is just a ball, and the information convex out of a ball is trivial. So there's no data. The data in X is invisible to Y and vice versa. We demand that the intersection between X and Y is generic. This is a simple condition. It just means that if you deform the regions X and Y a little bit, the topology doesn't jump. And then finally, we demand that X cuts Y into what we call a natural partition in the canonical state with respect to X. So this is the state that reduces to the vacuum on X. And what I mean by cuts into a natural partition is the following. So here's a useful visualization. So here's Y, and Y bar is its complement, and here's X, and X bar is its complement. Divide X into its thickened boundary and its interior. So that's these lines here. This is the thickened boundary of X. Then the so-called B, the intersection of the thickened boundary of X with Y, and D is the complement of the thickened boundary. Then we demand that this entropy combination in the state 1 sub X vanishes. So that's what I mean. That's what I mean by a natural partition. And it's, this is maybe it's not obvious when this will be satisfied. But by now we've gotten pretty good at using the axioms to study this combination of entropies for various regions. Okay, and so this is a slightly complicated seeming definition. It's the result of many iterations, and we think it's a good one. And the reason we think it's a good one, despite its complexity, is that there are many examples. So okay, so the first example is the torus, which I've drawn here. So it's not hard to check that this combination of entropies for the annulus vanishes. And so this is an example of a pairing manifold. And you can see that AB is a ball, and so on. All of these conditions are satisfied. Similarly, it's true for a genus G Riemann surface. You can cut it in half horizontally, you can cut it in half vertically, and check these entropy conditions, and they're true. And S2 times S1 is a pairing manifold. And the two ways of cutting it in half are, so one way to visualize it is think of it as, here's a sphere and here's a sphere. And so think of this as a sphere shell where I glue together the inner sphere shell and the outer sphere shell. So the circle goes in this direction from inside to outside. And one way to cut it in half is just to cut out an interior sphere shell. And another way to cut it in half is just to slice it like this. So this is actually a solid torus because it's a disk times a circle. And if you look at the intersections of these regions, you can check that these delta BCD conditions are all true. This connected sum of S2 times S1s, which was made from a ball minus G balls and a genus G handle body, is also a pairing manifold. This cylinder with gap boundaries is a pairing manifold. In fact, there are examples of manifolds that are pairing manifolds in two different ways, meaning they admit two different conjugate sets of decompositions. Not everything is a pairing manifold. An important example is T3. So there are three obvious ways to cut T3 in half. So if I draw T3 as a cube with opposite sides identified, I can slice it along X or Y or Z. So let's suppose we wanted to make it a pairing manifold with respect to the X slicing and the Y slicing. The problem is that the intersection of the X slice, sorry, this is the X slice, this is the Y slice. The intersection of the X slice and the Y slice is a solid torus and not a ball, and so it violates the definition. And similarly, a pair of pants, you can cut it in half in two different ways, like you can cut it this way and you can cut it this way. but the intersection of those things is not a ball. So not everything is a pairing manifold, but there is sort of a bewildering array of examples. One question that you might have is, suppose I give you some region X associated with some class of excitations that you like, how do I figure out what is Y? What is the region that it's paired with? And the answer is that the region Y is homotopic to the union of two operators that create the extreme points of Y. So for example, so here's the annulus. The operator that creates the extreme point of Y is this open string. If I join two of them together, that thing is homotopic to an annulus. Here's the what is it? This is the solid torus. Its excitations are created by this membrane. If I join two of these together, I get a sphere shell. That's the thing that's paired with the solid torus. Similarly, the sphere shell is the excitations are created by a string operator. Pairing two of those together gives me something homotopic to the solid torus. So I hope you see the pattern. A more complicated example is this torus minus the ball. In that case, the excitation is one excitation is created by this thing, which is a half membrane, half string. Two of them together has the same topology as the torus minus the ball again. And so the torus minus the ball is paired with itself. Okay, so that's the idea of given X, what is Y? And here's a table of the examples that we've studied so far. So I don't want to belabor the details of the table. I just want to highlight that there are many examples of this somewhat complicated definition. One that I'll highlight is this in three-dimensional bulk is this connected sum of many copies of S2 times S1, which pairs those graph excitations that I highlighted at the beginning with the excitations associated with the ball minus G balls, which is a cluster of G particles correlated with each other. Okay, so we've made a complicated definition and shown that a bunch of examples fit into that definition. And so what can we learn from that? So here are a few immediate consequences of the definition. The information convex set of X is isomorphic to that of X bar. And moreover, in each sector, so if I fix A as a label on the boundary of X, then the fusion spaces of X are the same as the fusion spaces of X bar, and similarly for Y. A statement that in the next slide we'll interpret as the statement that the S matrix is square is that the sum of the squares of the fusion dimensions of X is the same as the sum of the squares of the fusion dimensions of Y, and these are each individually equal to the dimension of the fusion space of the closed manifold, the number of ground states on the closed manifold. So this is the crucial relation that we're going to use to learn about the S matrix. And before we interpret it that way, one thing to note is that it actually provides some very powerful counting information. In particular, it counts these genus G graph excitations for arbitrary genus in terms of the fusion dimensions of the ball minus G balls. So which is to me a pretty non-obvious relation. And then finally, the topological entanglement entropies interpreted as the total quantum dimension agree between X and Y. So that is, if you compute the total quantum dimension of the excitations associated with X, it's equal to, so that's the topological entanglement entropy associated with X computed from X. It's the same as the corresponding object computed from Y. Okay. So let's work our way up to the S matrix. So this reference state, so given some pairing manifold, the reference state that reduces to the vacuum on X is a minimum entropy state on X. There's a sort of uncertainty principle, an entanglement uncertainty principle, that says that on a pairing manifold, if I reduce this reference state on X, if I consider what's its reduced density matrix on Y, on the complementary subregion, that it's a maximum entropy state. And the same follows if we switch the roles of X and Y or X and X bar. And the idea is very simple. It follows from the fact that Y cuts X into a natural partition, which in the state 1 sub X satisfies this identity. And as in its use in the axioms, this implies that for any region A outside of BCD, this state is a quantum Markov chain between A and C conditioned on B. So B is behaving like a buffer. And so let A be the rest of W besides X. So it's W minus X. So in this picture, it's the rest of this annulus. It's the rest of Y. So think of this is X, that's BCD, and this is Y. So Y is equal to ABC sub Y. And strong subadditivity says that that's, I got this inequality row. Says that this is the conditional mutual information. This is a conditional mutual information of a decomposition of Y. And it says that the state of Y is a quantum Markov chain, which is the maximum entropy state consistent with the marginals. But the marginals, AB and BCY, are balls. And so it's the maximum entropy state, period. And so that's this statement. So so given a state on the pairing manifold, a global pure state on the pairing manifold, if I pick a state where X is in a minimal entropy state, say X is in the vacuum, then Y is necessarily maximally mixed within the information complex set. And so this allows us to define the S matrix for the following reason. So consider a case where both X and Y are sectorizable. Then this formula for the dimension of the ground state space of M simplifies because these dimensions are just one. And so this is just the number of extreme points of Y. And the number of extreme points of X. And so extreme points of X provide an orthonormal basis for this ground state subspace of M. The way to think about it, so suppose X is this ball and Y is this solid torus, then I got these backwards. These two pictures are supposed to reverse. So suppose I specify the state in the interior of X to be alpha, that's an extreme point of X, then I can make a pure state of all of M by merging it with its complement and then filling in the hole to make a state in the Hilbert space on M. And similarly, if I specify an extreme point of Y, I can merge it with its complement to make a different orthonormal basis of the same Hilbert space. And so the S matrix is just the unitary matrix that takes one basis to the other. So it's manifestly unitary because it's just a basis change. The thing that's not obvious maybe is that this is what we usually mean by the S matrix, but thanks to Tarun, it is, because this, as I just explained, the states alpha X here are minimally entangled states along X. And the states alpha Y, A sub Y, are minimally entangled states along Y. So these are, with respect to two different sets of minimal entangled states, the overlap between them is a good definition of the S matrix, according to these folks. So far, there's an ambiguity of rephasing each of these states that I haven't fixed yet. And we can do that because of the uncertainty principle. So in particular, the fact that when in the state alpha X, the state of Y is the maximum entropy state, means that we know an explicit expression for that in terms of the quantum dimensions. And so in particular, the first row of the S matrix is given by this, which is not zero, and the first column is given by this, which is not zero. So we could fix the phases to make those real. Okay, so that was sort of the simple case where both X and Y are sectorizable. Let's consider the case where X is still sectorizable, but Y is not. An example of that is the cylinder with two gap boundaries where X is the half annulus, that's sectorizable, but Y is this half annulus cut by the surrounding the entanglement, surrounding the gap boundary, which is not sectorizable. So the extreme points of X still provide a basis. So there's one basis of the fusion space, which is labeled by extreme points of X. But now, in order to make a state of M, we need to glue a state of Y to a state of Y bar. A state of Y is labeled by some I index in the fusion space of Y with a particular boundary label. The boundary labels between Y and Y bar have to agree. And so another basis of this Hilbert space is given by a state with these labels. So it's labeled by Aij, where I and J are labels in the fusion space of Y with fixed A. And again, there's a basis transformation that takes one to the other, but now it has more labels. An example of an S matrix with such labels, actually in this very example, was studied by Janet Hung in this really nice paper. And again, we can partially fix the phase ambiguity because the uncertainty principle says that 1 sub X is a sort of maximally entangled state between y and y bar. It's the maximum entangled state within the information convex set. And this means that the first row of the S matrix is proportional to delta ij on these indices. So we can't quite fix all of the phases, but we can fix most of them. Okay, so having made this complicated construction of pairing manifold, let me give you a few payoffs. So one payoff is that it gives an answer to the following question, which is why is the total quantum dimension of the excitations, why can you write that as a topological entanglement entropy? Why can you write that as a conditional mutual information? So the total quantum dimension of some associated with some region is, let's think of that as the entropy of the maximum entropy state minus the entropy of a minimum entropy state. And so why is that related to a conditional mutual information? And the pairing manifold gives an example, gives an explanation. So it says that we can decompose X into BCD. So here's X. C is the interior of X. B and D are the thickened boundary of X. B is the part that intersects Y. And A is the rest of Y. This natural partition means, here I got the inequality right, means that this vanishes. And then using strong subadditivity a couple of times, this says that the state of Y is a quantum Markov chain. And so in particular, the maximum entry state on Y has vanishing conditional mutual information, which means that the conditional mutual information of the minimum entropy state on Y is equal to the difference, because the maximum vanishes, which the definition of conditional mutual information has these four parts. The first three parts actually are all the same between the minimum entropy state and the maximum entropy state, because this is a ball, this is a ball, this is part of a ball. And so those all agree just because of being part of the information convex set. And so the only part left is this difference of entropies, which is this TE. So for any manifold that which we can prove is a pairing manifold, it's just there's a TE associated with it, which we can understand in this way. Okay, I'm running out of time. So we've actually learned a bit more. So let me just summarize in one slide one other important aspect of what we've learned, which is about flexible operators and the Verlinde formula. So I promised that there would be Verlinde formula. So it's possible to show using the axioms that on a given region there's a set of flexible operators, meaning that you can deform them freely within the region, which create from this reference state the state on the pairing manifold associated with an arbitrary extreme point of X. And moreover, these operators form an algebra. So there's some structure constants of that algebra, which we can define in that way. And by studying this matrix element of those flexible operators between the two different bases associated with bases of the Hilbert space of the fusion space of the pairing manifold, in two different ways we can show this Verlinde formula. So it relates the S matrix that I just defined to these structure constants of the algebra of flexible operators. And notice that it's a sort of funny, in the case where Y is not sectorizable, it's a sort of funny version of the Verlinde formula, because the S, I want you to regard S here as a matrix on the IJ indices, and this is matrix multiplication of those indices followed by trace. So this structure was first appeared in this paper I mentioned by Janet Hung. And one thing to notice about that is that if Y has non-trivial fusion multiplicity, so those IJ indices are indeed non-trivial, then the algebra flexible operators of X is non-abelian. That is, these things don't commute with each other. F alpha beta is not F beta alpha. Associated with the same pairing manifold, by interchanging the roles of X and Y, we get a second Verlinde formula, which, where the two sets of indices are reversed. In the case where X and Y are the same, there's only one formula, but in general, X and Y are different things. In some cases, not all, we can show that these structure constants, which appear on one side of the Verlinde formula, are in fact positive integers, are now negative integers, because they're related to fusion dimensions for some region. It's an open question to show that in general, and it's not actually clear that it's true. Okay, so my final, I think I have two slides left. Let me just quickly comment about what I said about the mapping class group. So in the case of 2D anions in the bulk, the braiding operation is associated with the exchange of the two cycles of the torus, right, which is an element of the mapping class group of the torus. But the mapping class group of S2 times S1, the part that preserves orientations, for example, has two Z2 generators, one of which is just reversing the orientation of both factors, and the other which is like a 3D analog of the Dane twist. It's I did here's an explicit expression for it. So you do a rotation. So as you go around the circle, you do a 2 pi rotation of the sphere. And neither of these things is related to the braiding statistics between particles and loops. I think this thing is likely related to the statistics, which, whether the particles are bosons and fermions. It's the fact that it's a Z2 operation rather than an infinite order operation, like in 2 dimensions, is related to the absence of anions. But neither of these is the S matrix. In 4 dimensions, associated with the pairing manifold S2 times S2, you can again exchange the two S2s, and so the S matrix is again associated with the mapping class group. But in general, it's not. Okay, final comments. The story should be able to generalize to the punctured S matrix or the defect S matrix, where we think about braiding of excitations in the presence of a defect or in the presence of another excitation. The number of extreme points of X and Y in that case, just for example, in the case of the annulus with the defect inside, is no longer equal, but surprisingly, there's still a square S matrix that can be defined. This requires some generalization. Understanding T3 and the general loop excitations requires something new because of what I said about the fact that these intersections are not balls. It's rather than a pairing, it's more like a triality kind of thing, where there's no one region which detects all of the excitations in a given torus shell, but rather there are 2 of them which together, 3 of them which together detect each other. And then finally, let me close with a sort of paranoid question. I mentioned that there are some closed manifolds that we can't make by this method. And you might wonder whether the manifolds that can't be immersed in the ball after removing balls are hiding some secret extra universal information that we might need. So I'm very interested in overcoming that obstacle. Okay, so that's the end. Yeah, thanks for listening.
Is there any question? Yeah, I guess we'll just thanks John again, and